Hey, welcome back. Ever stop and wonder how your computer can possibly juggle you typing an email, printing a photo, and downloading a file all at the exact same time without, just completely melting down? Well, today, we're going to pull back the curtain on that silent, super high-speed conversation that makes it all work. We're talking about computer input and output, or I/O. Let's get into it.
Seriously, just think about this for a second. Your computer's brain, the CPU, is tearing through billions of calculations every single second. It's just unbelievably fast. And then there's us, maybe typing a few characters per second if we're lucky. So how in the world does this super genius processor deal with the, let's be honest, snail's pace of the outside world without just getting bored and shutting down?
And this right here, this is the fundamental challenge of pretty much all modern computing. It's a classic case of just totally mismatched speeds. It's like a high-speed chase where one of the runners is a Formula One race car, and the other one, well, the other one is us. And this speed difference is absolutely staggering. I mean, we are not talking about a small gap here. Your CPU is thousands, sometimes millions of times faster than your keyboard or your printer. If the computer wasn't super smart about how it manages this, the CPU would spend almost all of its precious time just waiting. And that creates a massive system-clogging bottleneck. So what's the solution?
Well, the solution is basically this incredibly sophisticated management team that's built right into your operating system. It's a whole system, a whole hierarchy, designed specifically to handle these crazy complex communications, acting as both a buffer and a translator between the super fast and the super slow.
And here's a look at the structure of that team. It's called the I/O subsystem. You can kind of think of it as the master traffic cop and a universal translator all rolled into one. See how it's built in these layers? From the physical hardware way down at the bottom to the software your apps use at the top, its whole job is to make sure every single piece of data gets exactly where it needs to go, smoothly and efficiently.
And that's pretty much its official job description, right there. The I/O subsystem's one and only purpose is to make communication between the computer's core and everything else not just possible, but actually efficient. Without it, your amazingly powerful computer would just be this completely isolated and, frankly, a pretty useless box.
Okay, so how does this team actually do its job? It doesn't just have one trick up its sleeve. Nope, it's got a whole playbook with 3 core strategies it uses for different situations. Let's break them down. We've got polling, interrupts, and DMA.
So first up is polling, and this is the simplest, but oh my gosh, also the most annoying method. It is exactly like a kid in the back of a car on a long road trip just constantly asking, are we there yet? Are we there yet? How about now? The CPU just repeatedly, endlessly checks the device to see if it's ready. They call this busy waiting because the CPU is definitely busy, doing absolutely nothing but waiting. It is incredibly wasteful. Now, a much smarter way to do things is by using interrupts. As you can see here, instead of the CPU constantly nagging the device itself takes charge. When the keyboard has a keystroke ready, or the printer is finally done with a page, it sends a little signal, an interrupt, to the CPU. The CPU then gracefully pauses whatever it's doing, handles that one request, and then gets right back to its important work. So much better.
And this is the perfect way to think about it. It's just like an oven timer. You don't stand in front of your oven for 20 minutes just staring at your pizza, right? Of course not. You set a timer and you go do something else. That ding from the timer is the interrupt. It's a signal that just says, hey, I need your attention now, and it frees up the CPU to be productive instead of just waiting around.
But what if you need to move huge chunks of data, like a big video file from your hard drive? Even interrupts can be a bit slow for that. And that's where the most efficient strategy of all comes in, direct memory access, or DMA. With DMA, the CPU doesn't just wait for a signal, it delegates the entire job. It tells a special piece of hardware, a DMA controller, hey you, move this giant file from the disk straight into memory and just ping me when you're completely done.
This is really the ultimate form of delegation. The CPU is the CEO of the company. It's not going to waste its valuable time overseeing some big but simple delivery. No way. It hands the task off to a capable assistant. That's the DMA controller, and it gets back to doing the important, strategic work of running the whole show. The CPU is completely free, making the entire system run incredibly efficiently.
Okay, so we've got our strategies down. But how does the data actually get packaged up and translated during these conversations? Let's zoom in on some of the finer, but totally crucial details. So data can be sent in two main ways. You've got synchronous transfer, which is super fast and works on a shared clock beat, kind of like a perfectly synchronized orchestra where everyone plays at the same time. Then there's asynchronous, which is way more flexible. It doesn't need that shared clock and can just send data whenever it's ready. This is perfect for sporadic stuff like your mouse clicks or your typing. At the end of the day, it's a classic trade-off between pure speed and flexible convenience.
So, here's a question. How does your operating system, whether it's Windows or Mac OS, know how to talk to the thousands of different printers, webcams, and keyboards out there? Well, the short answer is, it doesn't. That's the whole job of something called a device driver. This is a special piece of software, usually written by the company that made the hardware, and it's basically the perfect translator. It tells the OS exactly how to speak the unique language of that specific device.
And this diagram just shows that role perfectly. Look, the driver sits right there in the middle, deep in the core of the operating system, and it acts as this essential bridge. It lets your software, your game, your word processor, communicate its intentions all the way down to the physical hardware. It's really simple. No driver, no communication. End of story.
So let's bring this all back together. All these different layers, all these strategies and translators, they are all working together in perfect harmony to create that smooth, seamless experience that you and I have every single day. So what's the big picture here? Well, it all starts with solving that massive speed gap between the brainy CPU and the rest of the world. The I/O subsystem is the manager in charge, using a whole toolkit of strategies, from the dumb but simple polling to the clever interrupts and the powerhouse DMA. And then, tying it all together are the device drivers, acting as translators for every single piece of hardware. This entire invisible symphony is what makes your computer feel so snappy and responsive.
Honestly, the next time you type a sentence and it just appears instantly on your screen, or you print a document without a single hitch, just take a second to appreciate the incredible, invisible negotiation that's happening behind the scenes. It's this constant, high-speed conversation between dozens of components, all managed so perfectly that you don't even have to think about it.
And that brings us to a final thought for you. We've pretty much mastered the conversation happening inside the computer case. But what's next? As all our devices get smarter and more connected than ever before, what do you think is going to be the next great I/O challenge that engineers will have to solve? Let me know what you think.
If you enjoyed this deep dive into the tech that powers your world, you know what to do. Make sure to like, share, and subscribe to Tech Talk 101 for more explainers just like this one. Thanks for watching.